So I'm Yu Hanling, Director of Environment Engineering at Cyclopure. So first, thanks to the organizers for hosting this conference and giving me this chance to introduce and present on our cyclodextrin-based absorption technology. So my talks today will focus on the performance of cyclodextrin polymer that we developed for the removal of PFAS from those kind of clean matrix and also challenging matrix, basically diverse water matrix environment. So I will probably quickly flash through this slide because everyone here probably heard about lots of PFAS in this two-day conference and probably originally know a lot about PFAS. So PFAS refers to a large group of per and fluorinated alkyl substances, which is a large and complex group of chemicals. So there are over 6,000 different PFAS structures has been already identified from our water environment. And because of their surfactant nature and extraordinary, actually, biological and thermal stability, they are persistent. Also, they are used widely in those household and industrial products, but also lead to their persistence in this kind of water treatment cycle. So they are very hard to remove with traditional biological treatment processes. So that's why those utilities and consulting firms are more turning to those more advanced treatment technologies like activated carbon, exchange resin, and reverse osmosis. But of course, if you want to use Oyster, because Oyster removes those suspended solids also very well, as you can tell from this one, probably they can also do a little for the PFAS removal through bioaccumulation. So activated carbon, exchange resin, reverse osmosis, these technologies, they all show some different degrees of effectiveness against some groups of PFAS, but they all have this kind of potential issues come along with their applications. Exchange resin and activated carbon, eventually they will result in a large quantity of those PFAS containing spent media that you need to get rid of and also to probably need further treatment. And reverse osmosis continuously provide those kind of rejected concentrates with elevated concentration of PFAS, which also require further treatment. So by developing cyclodextrin polymers, we are looking to provide actually a full train treatment that can bring PFAS from separation to full mineralization destruction. So cyclodextrins, they are derived from cornstarch, so they are cost-effective, eco-friendly, and also renewable. So because they are soluble in water, so we use a one-step polymerization to make insoluble adsorbents, Dexorb. So Dexorb features those 0.78 nanometer cyclodextrin hydrophobic cavity still in it, which can provide a good environment for PFAS binding. So surprisingly, in 1 gram of Dexorb, we have like over 300 quintillion cyclodextrin cups. So this leads to the high selectivity of our micropollutants because the well-defined sub-nanometer hydrophobic cavity in these cup structures, they provide a very good binding for PFAS, but also preventing those kind of binding of natural organic matters from TOC and also inorganic ions from TDS through size exclusion. So this create a good environment for resistance to those kind of fouling created by these matrix constituents. And this leads to rapid kinetics, high capacity, and also the well-defined adsorption mechanism leads to the simple and also easy regeneration for multi-cycles of reuse of Dexorb. Now we developed 2 versions of cyclodextrin polymers, Dexorb, which is widely effective against those pharmaceuticals, pesticides, and personal care products. And we also have a Dexorb Plus, which have a slight positive surface charge that can have enhanced affinity for PFAS uptake. So we provide those Dexorb and Dexorb Plus in both powder and granular forms. And they're also certified under NSF 61 for as a safe drinking water treatment components. So I want to spend a little bit more time on the unique feature of cyclodextrin polymer, so which is size exclusion and size inclusion. So this figure on the left side actually shows a technical version of how this host gas complexation works. So PFAS with a perfect molecular size can match very well into the hydrophobic cavity of cyclodextrin. While natural organic matters and inorganic ions are either too large or too small to fit into the cavity. So the figure on the right side is a preferred animation to visualize actually how this kind of property of cyclodextrin polymer differentiate them from those traditional adsorbents like activated carbon. So activated carbon, it's shared the similar adsorption mechanism, hydrophobic interactions with Dexor. But because of its naturally occurred, those kind of uneven distributed pore size, there are a huge competition for those organic ions and for those organic compounds to compete with PFAS that they are originally probably as a background natural organic matter to compete for that. So this will significantly reduce the capacity on activated carbon for the uptake of PFAS. While on Dexor, those kind of even and uniform sub-nanometer size cup size provide a very good active sites for the selective uptake of PFAS. This actually not only lead to this kind of increased capacity on Dexor, but also provide its equal performance from those kind of simple and clean drinking water matrix to highly complicated landfill leachate, for example. At the same time, this also provides a good environment for easy regeneration. So in the previous slides, hopefully it's a brief introduction for you to understand our technology and also PFAS a little. So in the following slides, I will walk you through some of the performance data that we collected in different projects. So this slide summarize actually the performance of Dexor for PFAS uptake in wastewater effluent, surface water, groundwater, and a complicated water environment in the batch setup configuration. So it's a batch absorption configuration. So on this figure on the left side, it shows the PFOA and PFOS percentage removal in 3 different water matrices with a distinct level of dissolved organic matters, which was treated as actually a major components that can compete for the capacity on activated carbon and other sorbents. So as you can see from the first observation is that after 5-minute contact time and 24-hour contact time, the removal is almost identical in each of the water matrix, which indicating the rapid kinetics is maintained across all of different matrices, regardless of matrix effects. And at the same time, the PFOA removal in wastewater, surface water, groundwater, they are almost consistent, which also indicating the resistance to fouling caused by those natural organic matters and inorganic ions, which is the same story for PFOS. The performance on the right side figure also shows the PFAS uptake at an elevated level of total PFAS, which is well above 2,000 ppt, and with a DOM, dissolved organic matter level, well above 5 milligrams per liter, even much higher than the wastewater effluent. But as you can see, it's still, Dexor still rapidly and efficiently remove most of those PFAS, regardless of channel lengths, and also at the same time, there's no difference in those kind of rapid kinetics, as you can see from this figure. So batch adsorption configuration is one of the major uptake treatment processes. Another important treatment processes is actually packed bed filtration in the pressure vessel system. So we also evaluated the performance of Dexor Plus in different projects in this scenario. So this slide summarizes the performance of PFAS removal by Dexor Plus in the drinking water from Massachusetts. And it's a very trace level of contamination, but still above their regulations for drinking water. So at a simulated EBCT of 5 minutes, the 5 micropollutants, 5 PFAS that has been detected in this water and regulated by Massachusetts has been well removed by Dexor. So we use a unit of specific throughput to evaluate the performance, which stands for how much of the water you can treat it with one unit mass of the media, which can be directly related to the cost. So in this figure, you can see that 1 kilo of the Dexor is sufficient for the treatment, complete removal of all of these 5 PFAS from 60,000 liters of the contaminated water. And actually, at the end of the test, it still didn't break through to the level that's break the regulations of Massachusetts, which means 1 kilo of the media is sufficient for the treatment of more than 150,000 liters of the water. So, and it is equally effective against both short and long chain PFAS. And this is actually our lab setup to do the RSCT. So, drinking water is a clean and simple matrix. So if that's, it's not surprising to us that DexWork performs well in that kind of water environment. So this slide shows a much more complicated water matrices. So this is a groundwater needs to be remediated at Michigan. So it contains a very high level of oil and grease. So actually in the previous test, GAC and exchange resin has been tried in this water matrix, and they both break through earlier than it's expected in this water matrix. So I think the breakthrough occur in only several thousand of bed volumes pass through the column. But as we can see from the PFOS and PFOA breakthrough curves presented in these two figures, its capacity is still very similar, even at this kind of complicated water matrix. It's similar to what we see from the last slide in the drinking water treatment. So this provides a very strong support to the size exclusion mechanism as we introduce in the intro slides, and suggesting supporting this kind of resistance of DexWork adsorbents to the fouling caused by natural organic matters and inorganic ions. So this is actually the site, and because of the promising performance of DexWork in this water matrix, we are proceeding with the utility and also the consulting firm to set up actually a pilot test on this site. So, okay, if the treatment in this kind of groundwater impacted by industrial activities is not strong evidence enough to show the superior capacity of DexWork, now how about landfill leachate? So landfill leachate originates from this kind of old landfill site because of precipitation and degradation of the biomass. There will be those kind of liquid phase accumulated above, at the bottom of the landfill site and above the separation layer. So they need to be discharged periodically for treatment. And after, it's generally typical, those kind of reverse osmosis, multi-stage filtration to treat those landfill leachate so they can be discharged into the municipal wastewater treatment plant. So generally, adsorption technology is regarded as useless in the treatment of landfill leachate. But to try, we actually collaborate with a consulting firm, and they have contacted their own third-party lab to evaluate the performance of DexWork for the removal of the full panel of the PFAS detected in this landfill leachate sample from New York to see our performance. And as you can see, with this kind of crazy high level of TOC and TDS, we still see a rapid kinetics and high capacity. And it also shows some effectiveness for those kind of most challenging PFAS, PFBA, in this kind of garbage juice. So through the performance data, we can kind of conclude that we can achieve some insights on the equal performance of DexWork across different water matrices for PFAS removal. And it's also effective, and all of the advanced features has been retained in those kind of two configurations, both batch adsorption and also column adsorption. But as I mentioned in intro slides, what we want to provide is actually a full train treatment processes. So actually separating PFAS from the liquid phase with DexWork is only the first step that we want to do. After the exhaustion of the DexWork packed column, the spent DexWork plus column can be regenerated at a centralized site that we offer to our customers. And the regeneration solution will be limited in the quantity to fully regenerate a spent column. And at the same time, we only need ambient temperature. We don't need to increase the temperature to achieve a fully regeneration. After the fully regeneration, the regenerated vessel will be sent back to utilities for the next round of use, while the regeneration solution will be evaporated and to get the solid PFAS, while the regeneration solution will be reused. The solid PFAS will be mineralized and destructed with our EPA-funded mechanochemical processes.
1 minute left.
So at Cyclopure, we also care about the future. So, the PFAS that under regulation or proceeding to be regulated, they're only a small fraction of those or PFAS. As I mentioned in the intro slides, there are over 6,000 PFAS structure has been identified. So there are a huge group of emergent PFAS, zwitterionic and non-ionic PFAS that also need to be treated in the future because some of them are precursors for those anionic PFAS. Through collaboration with academic labs, we have 2 recent publications evaluating the PFAS performance for the removal of zwitterionic, anionic, and non-ionic PFAS in this kind of water. And this shows equal effectiveness against also those emerging PFAS. So in the future, we are hoping to extend our current full train treatment to solve the PFAS issue for also those kind of emergent chemicals. So thanks for your attention.